So salam sejahtera and have very good afternoon to all ladies and gentlemen. So welcome to the GSM talk. So I'm Lin Chinggit from Department of Geology, UNT Malaya. So today we are very honored to have Prof. Liviu Matenco with us. So he will be sharing his work on quantifications of sedimentations and diagenesis in tectonic setting. Okay, so before we start this talk, so allow me to introduce a little bit of background about Prof. Matenco. So Prof. Matenco did his bachelor and master degree in the University of Bucharest, Romania, and then in 1997 he did his PhD in VU University Amsterdam, the Netherlands, with a title on tectonic evolutions of the outer Romanian Carpathians constraint from kinematic analysis and textural modeling. So Prof. Matenco's research area is on sedimentary basin formation and evolution, okay? Long-term sediment dynamics and coupling with anthropogenic systems, orogenic structures and coupling with sedimentary basins, lithosphere dynamics, evolutions of tectonic-driven sedimentary sequence, source to sink. Okay, so Prof. Matenco is currently a professor in Utrecht University. He is the chair of the tectonics and sedimentary basin in the Faculty of Geosciences, and he is also the editor-in-chief for the journal Global and Planetary Change. Yeah. Okay. So without further ado, so allow me to welcome Prof. Matenco for his talk. So please, the floor is yours, Prof.
Thank you for thank you for this invitation. It's a pleasure to speak again at the Geological Society of Malaysia. I think my last talk was I'll try to speak loud for the one. Do you hear me online? Good enough. Okay, I'll try to speak loud for the online audience. Last time I was speaking about core complexes and a lot of metamorphic stuff. This time I will speak about sediments and basins. And my training is basically a structural geologist, but I got involved with many other people, including sedimentologists. Maybe you know Bilal. Bilal Haq is a well-known, let's say, sedimentologist. If you don't know him, then think on the Haq curve, sea level variation curve. That's the guy. Okay. And I work also with the diagenesis sedimentologist involved in diagenesis. And this is my colleague from Utrecht, and he works in also in IFP, Fadi Nader. And what I'm going to show you today is our having fun with sediments. And just if you want, three guys meeting and having a nice chat on how can we characterize better the tectonic sedimentation. And basically, this is a very simple cartoon image that most of you know, which shows you the settings of various types of sedimentary basins, either at passive continental margins, where the sediments bury a former rifting structure, or the active margins in front in forearc basins on occasional wedges, or in retroforeland basins, compressional or extensional backarc basins, or extractive basins. Yes. What do they have in common? All these basins have just one element in common, in the fact that you have the sedimentation is more aggressive towards its margins, and the sedimentation becomes less aggressive and therefore becomes deeper water in their center. It's very difficult to characterize these basins by using sequence stratigraphy Why? Because sequence stratigraphy has one very clear element in common. Everything refers to the coastline. Okay, many of these basins that they do not have a sea level in the classical way of understanding, because they can be situated on top of the mountains or very deep into the oceans. And sequence stratigraphy also assumes that the input of sediments is unidirectional from the continent to the oceans, while in tectonic active basins, the sediment input can come from multiple directions. Therefore, it's very difficult to use sequence stratigraphy terminology to characterize tectonic active basins. Okay, and it's also biased by sequence stratigraphers, which define tectonics as being relevant only to the third order cycles. They refer in here 1 to 3 million year cycles. Okay, and this is incorrect, because actually tectonics is relevant at all time scales. Yeah. So this is a typical diagram which we do in Earth Sciences. So if you don't understand what your data are saying in any field of Earth Sciences, then make a log-log plot. Log-log plot, so logarithmic scale in both senses. And then any kind of geological process will become linear. Okay, this is done, such diagrams are done by many other colleagues in climate studies, in sedimentology, in paleoceanography studies, in many proxy studies. So if you do this, then you realize that tectonics acts from the scale of the seismogenic cycle to the scale of fault activation, individual faults, sub-basins, basins, and then you can go to mega cycles of Wilsonian cycles, if you want, okay, from the Wilson cycle. And then if you plot all the other factors, you realize that some other factors are a bit more limited in influence. Okay, for instance, the glacial isostatic compensation, either instantaneous due to elastic compensation or viscous to the viscous mantle flow. Mantle-lithosphere interactions are million-year scale. Okay, the age of oceanic crust or ridge production scales, or even sedimentation is in geologic type of sedimentation is quite large scales if we ignore more or less the active sedimentation that we see today. Now, is this relevant? I mean, and how can you characterize this, let's say, this type of fault-driven sedimentation? Now, what is, and if you make a comparison with the absolute sea level changes, eustasy is basically driven by a number of factors, okay? For instance, the capacity, the container capacity of ocean, the groundwater capacity, the ice capacity, the capacity of ice to retain water, rivers and lakes, atmosphere and biosphere. Okay, so this is more or less what drives the absolute sea level variations. But if you calculate the amount of changes that you can do with various factors, you realize that actually all the sea level variations are mostly controlled by the ocean container capacity. Yeah. While all the other factors have minor influences, including sea level variations that we observe due to climate, which are in the order of maximum 100 meters. Yeah. While the container capacity of the ocean is controlled by tectonics and can make changes in the order of kilometers. Yeah. And by looking in this way to this kind of processes, you realize that actually sea level is an effect, is not a cause. Yeah. So you can define sea level as an effect, not a cause of changes in the observed sedimentation. It's an effect of a number of various parameters. And you have to realize that the scale of these parameters is highly variable. So if you want to understand it, you need to do multi-scale studies. That's just an example for glaciations. Okay, when the response to glaciation or deglaciation is dual. Okay, the elastic loading response or unloading response to glaciation is almost instantaneous. It's years to tens of years or hundreds of years, while the viscoelastic response is completely different. It's in order thousands to tens of thousands of years. Okay, so just if one cause, okay, can have a response which is completely different in time. Therefore, in order to understand the response of such processes, we have to use a multi-scale, multi-temporal, and multi-temporal and multi-spatial analysis of this kind of processes. Now, another example, dynamic topography. Everybody knows what is dynamic topography? Who knows what is dynamic topography among students? Students, what is dynamic topography? Anybody knows? Never heard of it? It's a relatively new term invented by geophysicists. Blame Harry for this kind of terms. It's a topography created by sublithospheric processes. So not lithospheric, not subduction processes, sublithospheric processes. And that's a typical example of the elevation of South Africa, which is very high elevation, a plateau type of elevation, but this is driven by a huge mantle plume from below. Okay, there's a huge mantle plume below which keeps this elevation, has kept this elevation for hundreds of millions of years. Yeah. Now, another example of negative topography is the one induced by the mantle circuits associated with subduction systems. And that's an example of a negative topography associated with the subduction slab, with the Farallon subduction slab in the Western Americas. Yeah. Just to give you a little bit of perspective of the variability of timescales that we need to take into account. In terms of sedimentation, you can speak about sedimentary basin systems or Wilsonian cycle systems, if you want, which act at the scale of the entire Wilsonian cycle, or Wilson cycle, yeah, which are 10 to 5, 10 to 6, sometimes 10 to 6, 10 to 9 years. So you can speak at the scale of an individual sedimentary basin system or an individual sub-basin in a bigger sedimentary basin. You can speak about individual faults creating the accommodation space, and faults, they are not instantaneous, they act over a certain time scale. And we can speak even at the individual fault activation moments, which are seismogenic cycles, yeah, where the repetitive seismogenic cycle is in the order of tens of years. Now, they all have the same elements in common. They create subsidence in one part of the system, where we usually define the basin. They might also create uplift in another part of the system. Yeah, and the tendency of people working in sedimentary basins is always to ignore the uplift because they don't see it. They have an unconformity over that. They don't know how to quantify it. Actually, there are methods to quantify uplift and erosion, such as thermochronology. Yeah, low temperature thermochronology can to quantify. Yeah, and why is that important? Because it quantifies the amount of sediments which can come in the basin. But very simply speaking, okay, the processes that you see in a basin are controlled by the balance between the rate of sediment supply and the rate of creating accommodation space. It's a very simple control. Okay, if the rate of creating accommodation space is higher than the rate of sediment supply, then what is happening? You go deeper. Yeah, your basin becomes gradually deeper and deeper and deeper. If the rate of sediment supply is higher, then you fill up the basin. It's becoming gradually shallower, shallower, and shallower. So that's the very simple definition of how a sedimentary basin system works. So if you take into account, besides let's say the simple sedimentation rate, a factor which is very often ignored in the analysis of a sedimentary basin is diagenesis. What is diagenesis? The students. What is diagenesis? Vitrification, one example. Yes. Cementation, another example. So the creation of rocks from sediments. That's diagenesis. Yes. Okay. And the diagenesis is influenced by a large number of factors, okay? Among which the most important is sedimentary facies, the flow properties, but also faulting and fracturing. Yeah, because faults and fractures are the most common pathways for fluid circulation into a basin. Yeah, and the cementation or dissolution next to a fault, yeah, it's enhanced. Why? Because you have a higher permeability next to the fault. It's very simple. Yeah, and you have to, diagenesis doesn't refer always only to cementation. It also refers to dissolution. So you can increase or decrease the permeability of a reservoir. Yeah, and this is also tectonically controlled, because tectonics creates a disequilibrium in the system. Yeah, creates a disequilibrium in the system in the sense that, for instance, deepening and sedimentation above will change from basinal fluid circulating in your sediments to compaction fluid released from the sediment. Yeah, good. Now, if you look, what is diagenesis and how can we define it? This is a typical diagram of a sedimentologist who doesn't know metamorphic processes, because actually, when you go somewhere around here, around 200 degrees, you already reach low-grade metamorphic. But then in any case, it depends on the diagenesis depends on the geothermal gradient, yes, and makes the separation between rock transformation due to fluid circulation, metamorphism. Actually, diagenesis is metamorphism. You can call it dissolution and precipitation type of metamorphism, okay, in basin systems. Now, diagenesis has been classically defined as being tackled differently in carbonate or clastic reservoirs. Yes, for instance, this is a very complicated diagram for carbonate reservoirs, defining the type of circulation into a basin influencing the carbonates, type of dissolution into the meteoric vadose zone. Okay, I will not bore you with this detail. The same thing is in siliciclastic system, with a difference. There is one type of diagenesis in dry climate and another type of diagenesis in humid climate, particularly the diagenesis in humid and warm climate, yeah, like we have in here. I mean, it's normal. I mean, you also know that the alteration processes, chemical alteration processes, are very important for climate. If you go in Sarawak and you build a road, yeah, after 50 years after you build your road, the entire rock on the face of the road is completely altered. Yeah. So chemical alteration is very important in this type of humid climate. Now, if you simplify everything, what does this diagenesis relate to? Relate to 4 types of fluids. Yeah. If the sediments are exposed, drains from above, yeah, and the rainwater has a different chemistry than seawater, and these are called meteoric fluids. Okay, they also have a different geochemical composition, allowing their fingerprint by geochemical analysis. The second type of fluids are basinal fluids. It's basically the seawater which interacts with the sediments above, which are below. Sorry. Yeah, it circulates to the very high permeability of unconsolidated sediments, and can create cements or can dissolve cement. The third type of fluids are compaction fluids. Yeah, loading sediments in a basin by overburden, okay, creates compaction, and the fluids are released from the compacting rock and interact with potentially with the rock above or rock below. These are called compaction fluids. Yeah, and the fourth type of fluids is fluids circulating on fractures. You can call them faults, fractures, joints, whatever you want to call them, but there is a very high circulation along this faults. Many times, sedimentologists or diagenesis people, they call them hydrothermal fluids. Why? Because they come from below, and many times they have a higher temperature. Yeah, but they're not really hydrothermal. Okay, it's just higher temperature fluids coming from below, or sometimes they call them juvenile fluids. Yeah, juvenile means They come from below. Pure fluids is coming from here. I don't really like this kind of. But if you want to make a separation on the influence zones of these fluids, you can make, for instance, here at the surface, a zone of influence, which is of the meteoric fluids, which you can define as a facies tract. Okay, it's very similar with sequence stratigraphy, where you define system tracts. Okay, in this case, you define facies tracts as being the zone influenced by the type of fluids. Yeah, this will be a meteoric, how do I call it? Meteoric diagenetic facies tract. This will be a basinal fluids, a basinal diagenetic system, a facies tract. Then you have a compaction diagenetic facies tract, and then you have fault fracture associated diagenetic facies tract. Okay, what do I mean? Fluid is one thing. The facies tract is the rock which is influenced by that type of fluid. Clear? I'm just trying to stimulate. Sorry. Now, if you want to understand how a sedimentation associated with a fault evolves, it's very simple. You create an accommodation, no matter what the type of fault is a normal fault, is a truss fault, is a structural fault, it doesn't really matter. One of the compartments will go down, the other compartment will go up. Yes? The compartment which goes down has, at the beginning, when the fault is very active, has a very high rate of creating accommodation space. So the rate of creating accommodation space is higher than the rate of sediment supply. And then what do you record? Subsidence. Okay. So basically the interface between water and sediments goes down. Yeah. It goes down not only in one direction, like you have in sequence stratigraphy, it goes down in all directions of the basin. Yeah. Because you can have a source area coming from one side of the basin, but you also can have a source area coming from the other side of the basin, or you can have a source area which is transporting along the side of the basin. So it doesn't matter from where you transport, everything is controlled by this balance between the rate of creation. Yeah. And we invented a name for this facies tract. Okay, we call it, which is a facies tract, is a sedimentary system tract, it's not a diagenetic system tract. And we invented the name for this facies tract. We call it sourceward shifting facies tract. Why? Because let's say the zones of sedimentation, they shift towards the margins of the basin. Basin becomes deeper, and then the source, let's say the zones separating the different type of facies, they shift towards the margin of the basin. Now, in the moment that the fault decreases its activity, the rate of sedimentation is higher than the rate of sediment supply is higher than the rate of creating accommodation space, and you start to fill the basin, and the limit between the zones of facies migrates towards the basin. That's why we call it basinward shifting facies tract. Okay, and this is a cycle. You activate again the fault, you make another two facies tracts. You activate again the fault, other two facies tracts. Okay. And in this definition, there is no time. You can apply it at any time you want. Yes? The only problem is that many times in the analysis of sedimentary basins, you see cycles juxtaposed. Can somebody give me an example of cycles juxtaposed on top of each other? Orbitally controlled cyclicity, how do we call this? It's a name coming from a famous Yugoslav, what is debated in Serbian or Croatian scientist. Milankovic, yes, this is a typical example of different temporal cycles. Okay, and many times when you look onto basin, you do not see that. What you see is this. No, sorry, I will come back. You see this. So basically, there are different order cyclicity superposed on top of each other. So this is a lower order cyclicity, for instance, the scale of an entire basin. And this is the higher order cyclicity, for instance, created by one fault in the basin. Yeah. So you see this zigzagging of cycles going up and down. Yeah. And then basically what you see is two orders of tectonic successions superposed on top of each other. Now, how can you relate this kind of cyclicity to diagenesis? I mean, it's not very difficult. If you are in the proximity of a fault, what type of fluids will circulate in the proximity of the fault? If it looks like a mushroom, it smells like a mushroom, it tastes like a mushroom, then it's a mushroom. So fault-assisted fluids. This is what you do. And in the proximity of a fault, you will develop the so-called facies-assisted diagenetic facies tract. Yeah? If you are next to the surface, close contact with the basin water, then the type of fluids will be basinal fluids, and you will develop a basin diagenetic facies tract. Remember that this type of fluids are detected by geochemistry, so you can make a separation between them. In the lower part of the basin, you have compaction diagenetic facies tract. And in the other compartment of the fault, which makes uplift, you can have meteoric diagenetic facies tract. Yeah? You can influence differently the rock with different type of fluids. That's my point. Did I lose you, the students? Are you still with me? Hey, I'm here. Are you still with me? So two concepts. One related to the faulting itself and distribution of sediments. So I go still first deeper and then shallower by filling the basin. Okay, and superposed on that, the type of diagenesis that takes place. Yeah? You like diagenesis? You should. It's a very nice process. Now, I saw this, and this will be with two orders of cyclicity, the facies tracts. Obviously, in the proximity of faults, you have the fault one. If you assume you have the meteoric one, basinal, and compaction. Clear so far? Any questions so far, students? I'm not asking the staff because they will phone me at the end. I'm asking the students if they understand. Good. That's an example. This is an example of the development of facies, of sedimentary facies in this kind of system, facies tracts. Okay. So if the entire sedimentation in here is controlled by one fault. And what you see is deepening, shallowing, deepening, shallowing, deepening, shallowing, deepening, shallowing, deepening, shallowing. And this is a sea level unconformity. Okay, so ignore this one. Yeah. So what is happening in here? The fault activates, you go deep, sediments come in. Okay, then the fault stops moving. You fill it up. Fault active again, deepening, fault stops, fill it up. That's a very simple process. Yeah. And many times you can directly detect this in seismics. This is seismic interpretation, what you see. What you see most often is this lobes associated with gravitational debris from the fault going towards the margin of the basin, going into the basin, towards the margin, or the center. And then you see a migration of mass wasting. You know what is mass wasting? Can you give me an example of mass wasting? Huh? Sedimentology, Dr. Mello's sedimentology. Turbidites. Yes? Debris flows. Various type of combined flows. I'm not, I should not go very far in here because I get punished by Mello. Yes. Good. So you see a migration of the turbiditic bodies, and you also see a migration of the pelagic sedimentation, which goes either fills up the entire basin or gets restricted in the center. Now, this, if you make a sedimentary column, this is how it looks like, for instance, in an extensional basin. These are the various people who have defined this kind of things, okay? This is the Ravnas' steel model, this is Prosser model, this is Katunano's models, which I don't really understand. And this is Garnius model, doesn't really matter. Any type of model that you wish for this type of sedimentation, you can convert it in that very simple concept, okay? Deepening and then fill up and shallowing. Yeah. The only thing is that these turbidites which come into the basin, they complicate a bit the view because they are mass transported from the margin of the basin. So I'm not referring here to the coarseness of sediments. I'm referring to paleobathymetries, absolute paleobathymetries. Yeah. Good. Same thing is in here. Continental, you go deep, there is climax, and then you fill up the basin with coarse deposits. And this model, Catunano's models usually assumes instantaneous development of a fault. So you make the fault instantaneous and then you fill up. Therefore, you don't have a source mode migrating glacier. But in this model, which is also Catunano, you do have. Okay, so if you want this finding upwards, coarsening upwards, finding upwards, coarsening upwards. The very simple way. But you should not look to the finding or coarsening, you should look to the paleobathymetry. This is the other way around. It assumes that the tectonics takes a very long time, and sedimentation is filling up is instantaneous. Okay, so here you don't have a basic migrating glacier structure. So this is how you can convert previous models in the models I'm speaking about. That's an example from field to show you that actually it can be more complex. This is from Torbas Basin in Spain. Anybody went to student field work in Spain? It's a very nice place. They have a good food, the tapas and so on. Oh, it's a very nice place. So I highly recommend for students. So what you see here is sequences of turbidites separated by unconformities. Okay, you have a prograding, retrograding. You have prograding, retrograding unconformities. Either how do you call it? Prograding and then retrograding, or the other way around, retrograding and prograding. Okay, different type of unconformity. And this unconformity separates different, let's say, facies tracts. Yeah. The difference is that in this basin, you steepen the fault, you activate the fault, you steepen the entire fault, you tilt and basculate the entire process, but then the very coarse debris comes when you reach the maximum, the slope instability angle. And then you have the mass transport deposits, okay? Big conglomerates coming into the basin, yeah? Coming from a storage which is in the shelf. So that's an example from the Torbas Basin. And then a complete succession will look like that. Fault quiescence, filling up, yeah? High displacement rates with coarse turbidites, and then the coarser deposits come at low displacement rates during the late stage. Why? Because you stiffen too much the slope, and you go beyond the critical angle of the slope deposition. Okay, students, you know what is the critical angle of deposition in marine environment? How steep can be a slope? The sedimentary depositional slope. Any ideas? Shall I call it 1 degree, 7 degrees, 20 degrees, 40 degrees? How much can you have a slope in the marine environment? Let's put it in clastic sediments. And roughly, if you have pure plastics, until 7 degrees max. If it's carbonate, then it can go to 30 degrees. Mixed, 15 degrees. So this is the typical angle of a slope. Depositional slope. This is an example of how you can model it in an integrated way. So what you see over here is basically a numerical model which models an extensional basin formation at the scale of the entire lithosphere. So you see that I start to activate, and the model creates an asymmetric basin because of a weakness zone implemented in here. So basically, you have exhumation, asymmetric exhumation of the footwall. And later on, we take the geometry of the basin which is created, and we start filling it with sediment. What you see over here, this is paleobathymetry, and this is sediment composition. Yeah. What you see here is cycles of progradation, retrogradation in the entire basin, which are actually cycles of fault activation and quiescence. So what do I do with the diagenesis associated in extensional basin? The diagenesis will act in different way, depends where you are. Close to a fault, you'll develop your fault-associated diagenesis facies. Yeah. If the fault in the footwall of an extensional of a normal fault, it has uplift, then you can have a meteoric diagenesis facies. You can have a compaction in the high rate of sedimentation, and we can have the basinal fluids acting much more in the areas of low rates of sedimentation. Now, let me show you a few examples, a bit more unusual examples, how you do this and why it's useful. So this is an example from the Dutch offshore, from the Dutch Central Graben. And the sedimentation in this offshore, also in the onshore, has a very particular feature, the one of thick salt, okay, in the middle of the sedimentary sequence. It's sectional salt, doesn't really matter what age it's permeable. Any idea what salt makes? The formation, the basin. If you have very thick salt, what's happening with the faults? When the entire sediments are buried. The faults are not transmitted to the salt. The salt decouples the formation. Okay? You look to this and you're wondering yourself, why is this called a graben? Any idea why it's called a graben? It's called a graben because of the faults visible below the salt. Because of this fault, this fault, this fault, this fault, this fault, which are normal faults, sorry, this one. These are normal faults which are active below the salt. They give the real geometry of a graben. But the formation above the salt is not transmitted by these faults. Why? Because the salt decouples the formation. Okay, salt is viscous. Okay, and faults are our faults. Brittle. Yeah, so you cannot transmit the formation of faults to thick layers of salt, and therefore salt will decouple the formation. Yeah, and the point is that the deformation that you see below the fault is not transmitted above, and the geometry above is different from the one below. The geometry of the normal faults. So you see that this normal, the maximum extension is along a fault like that. And above is very small. Actually, the maximum extension here is in this region. It's in the Jurassic sediments. Okay, and then how do you quantify the sediments over there? How can you make a prediction of the distribution of the facies? Then you can apply one of these models. And this is an example exactly in that situation where you use seismic, reflection seismics, and well logs, yeah, over there, to separate between cycles of deepening shallowing. Yeah. And actually, these are tectonic successions that you see over here. And the resolution that you can do this is much higher than any other, let's say, model, approximating model of tectonic evolution. And then you can say, okay, the continental facies that I see in this kind of, in this position, I expected to find it here, here, here. So what you are doing with this kind of model is facies prediction. Lateral reservoir prediction, continuity of your reservoir. Okay, so you can make prediction of distributions of facies starting from just very few data. Basically, you have seismics and a few wells. And in this area, you have only 3 wells. Yeah. So it's a very good method to make lateral facies predictions. And in this case. And this is a type of prediction looking to this facies over here, the seismic facies. And using the seismic facies and the well logs, you can make a prediction of how the distribution of sedimentology will look like. Okay, ultimately. And then you can also make a prediction on the link between sedimentation and the tectonic fault that you see below the salt. It's a bit more complicated settings, but I think maybe you get the image. Okay, in places where your faults are active and control the sedimentation, but they are not transmitted in an entire succession, you can make prediction of facies. That's the point. What do you do with the diagenesis? This is an example from the Dinansha carbonate platform in the Netherlands. Okay, so what exactly are you studying when you do diagenesis? Anybody can tell me? You look at the generation of cementation or dissolution. Yeah, that's an example where you see different generation of cement. This is one generation of cement. Actually, this is dissolution over here. This is the first generation of the cement, second generation of cement. Okay, and doing geochemistry on this cement, you can say which type of fluids have generated this cement, and therefore extrapolating laterally, you can make prediction on the permeability of your reservoir if it's carbonate. What do I have next? Yeah, that's an example of how you should work in trusting regimes. That's an example of pyramids. Okay, conceptual model applied to the pyramids. Basically, in rapid tectonic loading by thrusting, we have a thrusting in here and loads your basin and creates accommodation space. You have a migration of facies towards the mountain. The moment that the tectonics has a low value, okay, low substance or uplift, then the facies is either stable or prograding, fills the basin. Okay, after orogenesis, when you have a massive uplift due to tectonic rebound, you fill the entire sequence. So you can define this as the source migrating facies tract. This one is a basin migrating facies tract. This is the final basin migrating facies tract due to complete fill, terminal fill of the basin. If you want the molasses stage, everybody knows this term. Everybody know what molasses is? Flysch and molasses, you know this? Flysch, synkinematic turbidites, molasses, final regressive fill of a basin, of a compressional basin. That's an example from the molasses basin of the Alps in Germany, Austria, where you see, if you look carefully in the molasses, you see this cycles over here. Yeah? And if you analyze them very, very carefully, you will realize that these cycles, some of these cycles are created by the tectonic loading of the Alps. The Alp big mountain, they jump on the lower plate flexes down, you create accommodation space. Yeah. And there are also cycles created by major sea level event. In this case, it's an Oligocene sea level drop created by the closure of the Paratitis. Okay, so Paratitis was a big lake behind the Tethys. Okay, when you close the gateways, you can have let's say the lake level is controlled only by the balance between precipitation and the evapotranspiration, and then it can go up and down. Okay, it's not controlled by the sea level. Yeah, lakes, the mountains, the level is not controlled by the sea level, by the ocean's sea level. It is controlled simply by the balance between precipitation and evapotranspiration. Yes. And that's this event of the closure of the gateways of the Paratitis. Yeah, if you want to analyze the, let's say, the diagenesis and the fluid rock interaction, that's not that difficult. Basically, you have a large amount of calcification in the hanging wall of the truss. In the hanger of one truss, calcification second one of the truss, calcification over there, which are actually meteoric diagenesis facies tracts. In the basin, you have a compaction in the lower part and basin in the upper part, type of fluids. Yeah. And on the faults, you have a large amount of circulation of fluids, which will transform your, which will have an enhanced diagenesis on the faults themselves. And this is how such thing looks like. Okay, these are the type of cements that you can analyze. So if you look carefully, this is a carbonate. I think it's Spain, if I remember correctly. Yes, it's Spain. Okay. No, go for Oman. Sorry, my mistake. Okay. So if you look in here, you have 1, 2, 3 generations of cement coming on the fault plane. Okay. When this generation of cement come on the fault plane? When you have a disequilibrium in the system. Okay, and the disequilibrium is created by fault movements. So you can associate these various cements with different fault movement scenarios. 10 minutes left. Okay, very good. I bored everybody. That's another example in the, basically, if you want, this is my university. It's my university over here. I'm showing a bit of societal relevance over here. This is my university. And my university says, the bill for gas is very high. It's 20 million euros per year. This is how much they pay the bill for heating all the buildings of the university. And they say it's too high and we are not sustainable. The students protest outside, no more gas, no more gas. Okay, so, or no more oil and gas. No more drilling, no more oil and gas, they don't want this. So what do we do? How do you heat the buildings? Any ideas? Huh? Any ideas? How do you heat the building without gas? You don't need, I mean, in Malaysia, you need to cool the building. In this place to the north, you need to heat them up because it's outside is 0 degrees. Students, how do you heat buildings if you don't have oil and gas? Geothermal water.
Geothermal energy.
Sorry?
We can use geothermal energy.
Sediment energy, yes. Geothermal water. And this is an example. I mean, if the university would be clever, we'll drill here. And this is Rotligen, perfect Rotligen reservoir at 2.5 kilometers depth with temperatures of 85 degrees. You take the water at 85 degrees, you put it in a pipe system, and you can heat up all the buildings of the university. Or you can do another thing. Okay, but to understand the phase, you need to understand the tectonic successions which are over here. You need to understand the diagenesis of these things. Another example is this one, and this is exactly what they want to do. This is the power plant on top of the university. But to understand, if you look, what they want to do is to pump water in the summer at high temperature in a reservoir and extract it in the winter. Okay. And how do you create high temperature water? Is with solar panels. The summer, very simple. Costs you 0. Okay. And basically, the problem is that the reservoir is a bit complicated by this propagation system. You need to understand this propagation system and how it works and what is the facial distribution. This is below the university. And this is how you use the tectonic succession to make facial prediction. And in this way, you reduce the bill of the university from 20 million per year to 2 million per year with a 7 million euro investment. Sounds good? Sounds exactly very good. And this is telling you that the sustainable usage of the subsurface works. Okay, you don't need oil and gas. I'm not against oil and gas. Okay, nothing against. But I'm telling you there are cheaper solutions. And this is exactly the structure below the university. And if you look below the university, it's very complicated structurally. You have normal faults which are connected with truss faults. There are all kinds of faults over there. And you need to understand the facies below of your reservoir. Okay, so you need to do this kind of studies. Strike slip systems are no different. Okay, this is an example from the San Andreas fault. You know, the San Andreas fault bends around and has all kinds of transpressional basins. And in this kind of things, you can also define tectonic successions. Okay, you see the retrogradation and then progradation into the basin. Okay, it's exactly the same type of tectonic succession that you can define. And this is how you're looking in the cross sections. Moments of activation of the strike slip fault, you see them like that with fault-assisted diagenetic facies tract, also with compaction fluids and the others. This is an example. How do you see this kind of facies? This is an example of enhanced dolomitization on top of a strike slip. You see that it's not only on top, it's going also lateral the facies along this fault. This is the distribution of the facies laterally. Obviously, diagenesis can be combined with sequence stratigraphy on normal sequence stratigraphy in this kind of margins, and you can define this kind of facies tracts also with normal sequence stratigraphy in passive continental margins. Okay, I have too many slides, so I have to jump over some of them. That's another example of how you use it for understanding processes leading to seismicity. This is the big Groningen gas field in the northern Netherlands. It's the second biggest gas field in Europe, including Russia. Okay, and the government in the Netherlands and the companies have gained something like 400 billion euros out of this exploitation. But they had to shut it down. Why? And now it's completely shut down. Why? Because exploitation has induced earthquakes. And all the houses above at the surface are damaged by earthquakes. And nobody understands exactly how this works, because you need to understand how this fault works, because these faults are activated in the reservoir due to the reservoir depletion. And the big problem is that nobody understands exactly how the diagenesis works over there, the fluid rock interaction. Okay, what are the transformations due to the fluid rock interaction? And it's a study which is defining the type of cementation and the solution that you see over the dolomite, whatever, siderite. And ultimately, you can define this kind of fascias along faults. Okay? And interesting in this case is that you do not have, let's say, cementation in the fault core. Okay, why? Because it's filled with clay. There is no permeability. So the fluids do not circulate in the fault core, but they circulate a lot in the fault damage zone. And therefore, what will happen is that the reactivation of the fault is favored in the fault core and not in the fault damage zone, which is exactly the opposite that you would expect to a normal fault. The highest the offset, the bigger the damage zone. In this case, it's exactly the opposite. So that's why these faults are activated in the Groningen gas field. You want another example of how you can utilize this in practical situation? That's another example from salt subrosion. Anybody knows what is salt subrosion? Have you seen salt diapiers, at least in seismic lines? That, salt, there's these domes, which are diapiers moving to the surface. And every salt dome has a hat. Yeah? All salts, they like hats. This hat of the salt dome is called caprock. Yeah? And the caprock is formed by various processes. One of the most common is by the dissolution of the salt at the top of the salt diapir. So it's because of the hydrogeological circulation of the top of the salt diapir, you dissolve the salt and you leave only things which cannot be dissolved. Okay? In this case, what you have over here is anhydrite at the top of the salt. Anhydrite, which is highly fractured, high permeability. When the salt is reaching low levels, then you have a high circulation of meteoric fluids. Yeah? And then salt gets dissolved, but also anhydrite gets transformed. What's happening if you put, let's say, sweet water on top of anhydrite? Anybody knows? What's happening with the anhydrite if you put water on it? Becomes gypsum. And the transformation of anhydrite in gypsum is a transformation with an increase in volume with 15%, and therefore will fill all the permeability. So you transform a highly permeable anhydrite in impermeable gypsum. Okay, and this is a process which takes over all over again, and basically dissolves the entire cap of the diapir. I mean, in countries which have nuclear power plants, they need to store their nuclear waste someplace. Yeah, and one of the most common place is salt domes. They want to install it on the salt domes, but the regulations say that the salt dome has to be stable for 1 million years to cover the decay of the radioactive elements. Yeah. So where do you put it? You put it deep, which is very costly, or you put it at the surface, and then you are threatened by subrosion that will reach the let's say your storage place. So you need to calculate the subrosion. That's the point. And that's an example of a model. This explains subrosion. Sorry, I think I've shown you this. First of all, you need to restore the salt. And this is a model which solves the salt restoration. Yeah, and this is how it evolved over time. So for a very long time in the period, see, the salt has moved slowly and then suddenly very fast. This big diapirs have formed. Yeah. And then besides the salt diapirs, you need to model the salt. So what you do is a chemical model of suberosion. Basically, this is your salt dome. That's a model, huh? It's numerical modeling. This is your dome, okay? You have forced your water to circulate in this direction, create a hydraulic gradient, okay? And you put the salt, let's say the composition, here is salt, here is anhydrite, and then you have your salt, let's say water circulating in this direction, this is the amount of salt you dissolve. Yeah, this is in dissolution. The arrows, the color of the arrows means dissolution. Yeah, it's a fluid phase velocity combined with dissolution. And this is how you can approximate the solution. And this is an example of the meteoric influence on the sedimentary system. You always should expect such meteoric influence when your system is exhumed. Yeah. And it is a very useful calculation because people use it for something practical. In this case, to store nuclear waste. I forgot to show you. I mean, the rate of erosion is quite slow, actually, in reality. So you will dissolve something like 10 meters per million year. It's not that high. And it's decreasing as much as deeper as you go towards the base of the diapir. So the suberosion rate calculated by us for this kind of typical Dutch diapirs is around 10 meters per million year. So it's not very high. So we say that this repository might be stable for the next million years, but we need to do better calculations, a better model. Good. Now, the impact of diagenesis can be calculated in this kind of models, and you can put things on top of the other. This is an example of how you put on top of the other the meteoric, the fault-assisted one, or the meteoric and the basin one. Or you can combine the basin with in different parts of the basin. I mean, this boxes represents the places in the basin that you can want to combine. One direction is dissolution, and the other one is precipitation. Is this important? I think the importance of this is impermeability. Is your reservoir permeable if you move towards the fault, or the reservoir becomes impermeable if you go away from the fault? Yeah. And this is it's a process which is neglected by almost everybody. Okay, and they are wondering if they drill close to the fault, why the reservoir doesn't have permeability. Yeah, because of diagenesis. It's enhanced next to the fault. This is the same thing for the entire basin. And the controls on deposition are very similar. Okay, so you can combine the diagenesis model with the tectonic model of creating sedimentation. And then you have basically a complete definition of sedimentation and diagenesis in tectonic action. This is the combination. Basically, I start with the sedimentation model in here, uplift, subsidence, erosion, sedimentation, eostargy, facies tracts. And then I add on top the diagenesis for the various type of scenarios that you can imagine. And I think I already spoke too much because I see people completely crashed and sleeping. Okay, conclusions, takeaway messages. Two very simple takeaway messages. Basin diagenesis is the third major player in sedimentary basin and has very little process-oriented quantification so far. In the sense that you cannot use diagenesis, it's very, I mean, so far, people do not have predictive models to predict what is the diagenesis on the lateral on reservoirs or general sedimentary erosion. Yeah. And you can quantify this by using a tectonic driven model. Okay. Tectonic succession is my preferred one. Why? Because it's mined. Very simple. Okay. So you can use it in tectonic active sequence, or alternatively, if you don't like me, use sequence stratigraphic approaches, but combine it with a quantitative diagenesis model so you can understand what's happening with your reservoir. Thank you very much.
Okay, thank you very much, Prof. Matenco, for the interesting talk. So I would like to take question from the floor. Should we start with the online one? Later on, we come from the for the physical. Any question from the online audience? Please stop share. Feel free to unmute. Zoom.
Apologies, it took longer than I calculated. I got enthusiastic and I started to ask questions.
Sorry? Where is the presentation? Stop share. So down this. So we have the chat. So Prof, we have there's quite a few questions.
Let me try to do it.
Yeah, the first one by
Controls of thermal history, special exhumation where I contact substance. Yes, we do quite a lot. Or how do we do this? By modeling, by numerical modeling. So basically, we combine the sedimentation with the thermomechanical model, which predicts the thermal influence. I have some reserve slides which I can show, where we for instance, model the conductivity of a diapir, the thermal conductivity and the thermal distribution of a diapir, or we can model the, let's say, the thermal distribution in extensional basins with the anomalies that you create during lifting. Yes, we can do that. The backstripping model. Yes, basically, if you want to simplify to the extreme, that was a backstripping model. A little bit more complex because it's flexural backstripping. It calculates temperature. It calculates the it's a temperature-based compaction history and also fluid system. Yes, basically, it's a backstripping model. Any other questions?
Yeah, question from the audience here.
Come on, students, ask questions. Don't be silent. Remember, I'm not a teacher. I can tell you.
Hi, Prof.
There's a question online. Yes,
Yeah.
please.
Yes, so I want to ask some questions. How you calculated the subsidence and kind of the uplift movements? So using the seismic only itself, or
I mean,
some other
the substance we calculated standard by modeling, okay, by looking in the sediments and by modeling this. The uplift we can calculate by thermochronology, for instance, low temperature thermochronology. I mean, in my experience, for instance, in extensional basins, let's take one that you know, Malay Basin. Any idea how much exhumation you have in the footwall of the Malay Basin?
I don't know exactly what is the rate, but I know the.
I mean, you should use thermochronology methods. That's my point. The point if you use thermochronology methods, like they do it for the Norwegian margin, okay, then you get a much better estimate on the uplift, and this gives you a much better estimate on the fault evolution, okay, because you have massive uplift of the footwall, then your temperature distribution will be radically different than the one you calculate. In many basins, such as Malay Basin, people say that, let's say, the organic matter is over mature. This is just because they ignored the fault offset, which creates uplift, okay, exhumation of the footwalls. Yeah, so this is how we do it. We do it combined. We do it by structural geology methods and thermochronology methods, looking in the uplifted part, and we do it by standard basin methods, looking in the subsided parts. Did I respond to your question?
Yeah, and yes, sir. I have another one question.
Yes, please.
So where I seen your model, where the salt diapers model, you like a kind of backstripping model.
Yes.
So and also you accounted that permeability quantification. So how can you quantify the evolution of permeability evolution through the each strata by strata? And by the regional stress field, how you account it, the stress, hysteresis. These things we can.
Can you repeat? I'm sorry, I did not understood. It's not, the sound is not very good. Please repeat. The question only. Only the question.
Okay, the question in your model.
Yes.
How you account the permeability evolution by each strata?
How do I account for the evolution of the diapirs? Yes, I mean, you can account that simply by looking into the synkinematic deposition of the flanks of the diapir. You know, there's rim sync lines of a diapir. If you look in the rim sync lines of a diapir, you do have a very standard, a very clear and standard, let's say, development of tectonic successions. I think this is what we do quite standard. It's quite easy. We call them clown smiles, a clown who smiles. You know, a clown from the circus. We call them clown smiles, okay? And if you look there, you have a very clear synkinematic wedge, which looks like the smile of a clown, which half of it is a source migrating, the other one is a facial base migrating facial structure. So this is what we do for the ones which are associated with soul migration, usually in the early stages of evolution. In the late stages of evolution, we have this massive soul piercing of the entire system. This is a bit more difficult to quantify. Okay, and the only tool available for us to quantify is modeling like the one I showed you. And the modeling which I showed you assumes that the faulting at the base of the salt has to remain stable during this late stage piercing. Okay, so what we did is that we did the backstripping, obviously, a kind of backstripping, it's not really backstripping, but at the same time, we imposed that the faulting at the base of the salt diapir has to remain stable because there is no tectonics at that time. Okay, and by assuming a stable base of the salt, then we can quantify how much the diapir was pierced, has pierced the neighboring rocks. Yeah, did I respond to this question? I think we lost it.
Oh, it's muted.
It's muted. Okay,
So
thank you.
Yes, that is so. Yes, Prof. Thank you for your explanation.
Thank you for the question.
So
that's a very good question, actually.
So we have another question there.
Yeah, it's very simple. I mean, the question is what role do faults and fractures play in enhancing or reducing permeability during diagenesis? It's very straightforward. The faults are conduits, major conduits for fluid circulation. Okay, and depending on the type of the geochemical type of fluid circulating, it can reduce or enhance very rapidly the permeability. I have field examples, many field examples I can show with enhancing or reducing permeability. Okay, so if you are studying a reservoir and you are far away from faults, okay, you can make simple, let's say, approximation between places that where you have information. But in the moment that you go close to a fault, you should not take any assumptions. You should understand much better the evolution of fluids inside your basin, okay, to understand the geochemistry of the fluids, okay, so you call Professor Van Garcia, hello, Van Garcia, how is it? Okay, and then she tells you what is the geochemistry, and then you apply a geochemical model let's say, to understand if you have fault-assisted dissolution or fault-assisted precipitation. Did I respond to this question? Okay, probably. Yes, sir.
Okay, Patrick.
It's a simple question. I've seen scales and sedimentation zones in seismic wells. They pre-drilled, they appear as flat beds. So I'm just wondering, can scales and sedimentation zones be improved? Can be flat and short?
If you have, for instance, if you have like in the case I showed, okay? The case I showed you, fault has smeared the clay from the neighboring rocks. Okay, the smearing of the clay, okay, is made the core impermeable. Okay, so if you find a process which makes, let's say, the let's say the fault in parallel, and then the population will solve. Exactly. Just to give you an example, clays are self-healing. Someone is self-healing. So if you wound them with a fault, they heal themselves. Okay, this is self-healing. Okay, so if you create permeability with a fault, then the permeability is self-healing by expanding the space. Okay, so if you have a fault which is crossing through the carbonate, then you have a layer of grains. Okay, the fault offset is not very high. Okay, you don't put in contact, you don't offset the entire clay layer. Okay, so the entire clay layer will become impermeable because of self-healing. You have circulation of fluids in the carbonate, you have volumization, outside precipitation. Then there's a lot penetrating the horizontal zone. Very good question.
So this method actually have like a sense of it's equally possible.
Obviously, yes. Juvenile fluids can break carbonates from fluid-rich carbonates from below. They can cement the system. It's very common. Actually, we believe that large particles in carbonate sedimentation you see in sandstones is very difficult. Because you see it most of the time in active systems. Then if you go to any other questions? Good. Should be.
Yes, I have a question.
Yes.
In this
Yes, please.
area, like in this type of area, studies, we have so difficult challenge, which is how to separate tectonic signals from climatic signals in this geological studies. Do you know how to separate between the tectonic signals and climatic signals?
It's very simple. Geochemistry. There is environmental geochemistry, which tells you, which gives you the climate. You have a large amount of, let's say, proxies, such as clumped isotope proxies, which will give you directly the temperature. There are humidity proxies, which can tell you if you're working in continental environment, which can tell you exactly what the humidity was. So you start in this kind of, if you have a combination with climatic influence, then my advice would be to start with paleoclimatic studies to understand the, let's say, the variability. Just you can do it in just one borehole. Okay, like they do it very frequently for deep sea ocean drilling sites. Okay, and then you make your climatic wiggles. And at the end, you compare the climatic wiggles with the tectonic signal, which is also as kind of wiggles. And there are quite nice studies which see the let's say the superposed climate signal on the tectonic signal. For instance, offshore Australia, there is a very nice study which I can recommend. Did I respond to your question?
Yes, I understand. Also, I suggest if anyone want to get more knowledge about this one, to study about Taranaki Basin in New Zealand. It's very simple and very nice example.
Taranaki is a very nice example. Gippsland is also a very nice example, which is not very far from. I mean,
thank you.
All the basins around Tasmania are quite strongly influenced by climate. Taranaki is a very good example, correct?
Thank you so much.
Yes. Another question there.
Attendance, yeah. Online attendance.
Yeah, this is what the question is about the safety of nuclear waste. I mean, nuclear waste repositories are built generally, the ones which are being considered, as I know. Actually, there are two only built so far. One in the United States, another one in Switzerland. They are, I consider either salt or clay, just because clay is self-healing and salt is also self-healing. Yeah. And in the case of salt, what you say, it's exactly what was my point of the discussion. We need to calculate how much suberosion we have into the diaphragm. But these are very specific case studies in the sense that you have to look to a very specific diapir. Okay, Netherlands is not yet in the situation of defining a very specific diapir. Why? Because they are afraid that people will start protesting. We don't want a nuclear repository here. Okay? I mean, this is what is happening. If you want to do something, then people protest against it, no matter it's good or bad. Okay, so that's the. I mean, in the future, our study, which is generic, will have to become specific, and then you can make better prediction of subrosion. I hope I responded to the question.
Okay, no more question again.
Yeah, the problem is that the nuclear waste will not leak to the surface because salt is impermeable. Okay, the only way to leak it to the surface is to remove the layers of salt. And the considered technology is a bit different in the sense that you put your nuclear waste, then you put salt backfill. So you fill the entire space with salt. How do you call it? Backfill. And you add cementation solutions, self-healing solutions, which in time will transform the salt aggregate into the rock salt because it's self-healing. Yeah? The salt is impermeable, so will not link naturally to the surface. But you have to be sure that where you put your repository, I mean, you have to make a study that this is real rock salt. And it's quite simple. I mean, most of studies assume that you'll build galleries, mine galleries. So you don't just throw away nuclear waste in the well. No, you build a gallery which goes to 500, 800 meters into the salt diapir, in the core of the salt diapir, the area which is more pure salt. So we are sure that salt is self-healing and is impermeable. The only thing which you are not sure is how much can be dissolved by subrosion. And actually, in subrosion, the most dangerous action is the human action. Okay, it's a very, very famous case in Germany, in Gorlingen, where people have started. They have a big salt repository, not for nuclear waste, for other things. Okay, but people at the surface started to excavate. They remove all the cover of the salt. And what happened? The next river has started to dissolve all the salt. Yeah, and then we endangered the entire repository because the salt cover will collapse. And you have penetration of waste from surface. Okay. Salt caverns, in our experience and in our modeling, the natural processes acting on salt diapirs are much less dangerous than human processes. Humans are much more dangerous in nature. In nature itself. Other questions? Well, it's not tectonic activities. I mean, let's put it this way. We say that we haven't considered the possibility of tectonic activities on nuclear waste sites. No, it's not tectonic activity. I mean, but it's salt movement activity. The salt itself, when moves, it creates variability of the position on its flanks or above, which is exactly the same as the one of a fault. Maybe I should have explained this. So salt sink kinematic deposition, it's exactly the same as the fault kinematic. Any other?
Okay, I think that should be all.
One
So
more students. This one, no, this time. Yes. What is it? It's very simple because you want to predict reservoirs. We want to utilize the surface for various things. Okay, at the moment, we utilize it a lot to pump gas, oil and gas. In the future, we want to decrease that, and we want to utilize it much more for thermal energy, storage of hydrogen, or whatever the humans would imagine be sustainable. Yeah, this is what we want. We have a hole in here.
Okay.
We know the reservoir. The point is, how can I predict the characteristics of the reservoir from this point to that?
Okay, for online participant, could you kindly turn on your camera so that we can record the attendance or take a group photo? Okay, thank you so much.